In this final video, I will give you practical guidance how to implement neural networks in Pytorch. First, you will learn about the basic concepts of Pytorch programming, including what are Pytorch tensors, automatic differentiation using autograd, and training on CPU and GPU. Then, we will also learn how to implement regression and binary and multi-label classification using neural networks. Finally, we will learn how to implement nonlinear models using multiple layers of neurons. Pytorch is a popular Python-based environment for implementing and training neural networks. It is built using Pytorch tensors. Pytorch tensors are multidimensional arrays for storing data and network parameters. They are similar to NumPy arrays but have additional features, including ability to run on GPU and automatic differentiation or autograd. Here we see an example code how we can create a Pytorch tensor. By default, Pytorch tensors are stored on CPU, and we can test that by evaluating tensor.device. Here we can see that device type is CPU. Pytorch tensors can also be sent to GPU, for example, by using function tensor2CUDA. Now, when we test tensor.device, we see the type of the device is CUDA, which is GPU. What makes Pytorch such a powerful tool for deep learning is automatic differentiation called autograd. This means that we do not have to worry about calculating gradients for training, they are automatically evaluated. Here we show an example of how this works. Let's say that we have a loss a1 squared plus a2 squared. We would like to evaluate gradients of this loss with respect to a1 and a2. This graph shows how we can separate this process into individual steps. The top row of the graph shows how we evaluate the loss. First, we square each element of the vector a, and we obtain the vector b, and then we sum all the elements of vector b to calculate our loss. Note that the loss always has to be a scalar. The bottom row shows how the gradients are calculated using the chain rule. First, we calculate the gradients of the sum function, followed by the gradients of square function, and that way we obtain the gradients of the vector a. This process underpins the backpropagation algorithm during training of neural networks. And this is how we implement calculation of gradients in Pytorch. In the top cell, we implement calculation of the loss. Note that we have to explicitly set that the tensor A requires calculation of gradients. In the bottom cell, we call the function backward that calculates the gradients. The gradients are stored in a.grad. Note that these gradients are calculated for the specific values of the tensor A. We will now show how we can create a neural network in Pytorch. The simplest neural network will consist of only one neuron and identity activation function, which does not require implementation. Such setup will give us a simple linear regression. We will create a network class that we will call Artificial Neuron Regressor or AN Regressor. It is derived from the Pytorch class torch_nn module. We define the network architecture as a single linear layer with one input and one output, which will produce univariate linear regression. We also need to define the forward path, which will evaluate the output of the network. In the forward path, we will evaluate the linear layer for the input x. Finally, we need to create an instance of the network. Summary of the network architecture is printed here. Next, we need to define how we will fit this network to the dataset. To do that, we select the loss function, in this case, the mean squared error loss. We also select the optimizer, in this case, a stochastic gradient descent. We need to tell the optimizer to optimize the parameters of the network and also set the learning rate. We will train the network for a predefined number of iterations called epochs. Each iteration consists of 5 steps. First, we clear the existing gradients. Next, we predict the output of the network using latest estimated network parameters. Then, we evaluate the loss between predicted network output and true expected target values. Then, we perform backpropagation to calculate the gradients of all network parameters using the function backward. Finally, we update the network parameters. After we finish training, we can predict the target values using the forward pass. Here, you can see the plot of the fitted model. For regression models, we can evaluate performance by taking the square root of MSE loss function. Note that for tensors that contain gradients, we need to extract their data before we can perform further calculations or plotting. Let's now have a look how we can create more advanced network architectures. To create multivariate linear regression, we simply increase the number of inputs of our single linear layer to be equal to the number of input features. Because it is still a linear regression, we don't need any activation function and we will optimize the network using mean square error loss. To create a binary classification, we apply a sigmoid activation after the linear layer and define a binary cross-entropy loss. Note that the activation function is added both to the init and to the forward functions. This classifier will be linear because we have a single linear layer. To create multi-label classification, our linear layer will have as many outputs as we have classes. The loss will be the cross-entropy loss, which in Pytorch combines softmax activation function with cross-entropy loss. All of the networks that we have shown so far created linear models because they contain only one linear layer. We can create nonlinear models by stacking multiple layers one after another and placing nonlinear activation functions between them. In this case, we have 2 layers. The first layer has 2 inputs and 6 outputs and is followed by ReLU activation. The second layer has 6 inputs to match 6 outputs of the first layer and only 1 output, which is passed through the sigmoid activation to create a binary classifier. We will implement examples of the networks that you have seen in this lecture in the tutorial. In the first notebook, you will be introduced to Pytorch tensors, autograph, and implement a linear regression and binary classification in Pytorch. In the second notebook, we will implement multi-label and nonlinear classification models. In the third notebook, we will show the full training algorithm for neural networks, including validation and testing. In the fourth notebook, we will implement a single-layer perceptron ourselves. Before we conclude today's lectures, please test your knowledge using the quiz on Keats.